That is actually a different way of doing search that actually turns out to be what's called gradient search. We will talk about this later.
Is that on the website of the...
No, so in fact that's not even, so there is a difference between systematic search strategies where the best way of thinking about a systematic search is it has a search, it knows where it has been, so it will never again go back to those places, not infinitely often anyway. And local search strategies that we will talk about later, a great example of that is just follow the local gradient. Now when you follow the local gradient, you can be going in loops. But if you don't go in loops, then you might actually be way more efficient. In fact, the next class will talk a lot more about that. This is systematic search. It keeps track of where you have been. Okay? And yes, there was another question. Okay. One last thing. What happens if I can inscribe circles, I can circumscribe? Right? That's the two things that you learned in your geometry class. What happens if I circumscribe all the obstacles? What? So would it be admissible or not? No. So remember the last inadmissible heuristic I said was building walls, Trumpian like. But really, you could think of simpler ideas which also will be inadmissible. You don't need to build big walls. If you just, in this particular case, if you just circumscribe them, you're already guaranteed to overestimate the cost in some places. So it's not obvious. You need to make sure. So the difference between inscribing and circumscribing is in one case you are reducing the constraints to the motion. There are more places you are saying you can go through than the original problem. That's abstraction. In the other place, you are increasing the constraints to the motion. Because when you circumscribe, you are saying certain paths that were before feasible are not going to be feasible. And when you do that, obviously, you no longer have admissibility. Because it's not an abstraction. If it is an abstraction, you are admissible. If not, it's not. It's a pretty powerful connection to make. Yes?
Is this statement correct that if my time complexity for solving a problem is less than the time complexity for finding a heuristic for that problem, then what I'm doing is actually overestimating?
It's not obvious, no. We should talk about it, but that's not.
Then, how do you decide that if my program, the time I'm still spending, what I'm spending, nearing to x star and I should stop?
Again, that's the reason I gave it as a project instead of a formula. See what I'm saying? It's an art form, figuring out where this happy medium exists. And in fact, in science, biases of the scientists are much more vicious than any mistakes they can make. Okay? And this is important to understand that for the longest time when A-star search has been invented in 60s, for the longest time people just assume without any proof that if you're computing heuristics should be easy to compute. That's just the way it is. So they're mostly looking at heuristics in these areas. So the two heuristics you heard of for 8 puzzle is one is number of misplaced tiles. Doesn't really require a Nobel Prize to compute that. And basically Manhattan distance, which is also extremely cheap to compute. The assumption is that if you're computing heuristics at all, maybe the good ones will all be on this side. That's a bias. Nobody checked this. And in fact, one of the interesting things that happened in this area is finding that for many problems, things like pattern database heuristics, which are actually much costlier to compute, are better in the overall sense. That means the heuristic cost is somewhere here, but the search cost is driven down. Sorry, the heuristic cost is somewhere here, but the search cost is driven down enough that this is better overall. And if you know this, then obviously it's not a bias. And the bias of scientists are actually much bigger things. So in fact, it's very well known that one of the biggest biases. We are all scientists, but some of our biases don't matter. But the big guys' biases matter. The one that you all know, the famous bias is of Einstein. Right? Einstein basically never believed in quantum mechanics. And he basically said, God doesn't play dice with the universe. So as if he normally has a private line to the God, right? And so he was essentially looking only for theories that don't have stochasticity of the level that quantum mechanics brings in. Was he right in the end? No, of course not. He's a great guy, but he was wrong in this. And in fact, Niels Bohr, who was like the saint of the quantum mechanics side, one time apparently said in exasperation to Einstein, Albert, don't tell God what to do. Okay? So the idea is, in some sense, if you have biases of this kind, what will work and what won't work, and you don't actually check it, you could be wrong. You could be wrong not just individually, you could be wrong as a community. Okay? So right now, in fact, let me see if I can show you that, and that's probably the last thing we can actually have time to. No, I don't have it. So the pattern database heuristics essentially are a costlier way of computing heuristics for the missing tile problems, the tile puzzles, where they will assume that certain details of the puzzle must be true, but the rest don't matter. So for example, so for example, imagine I'm going to go from here to here. Okay, I might say that the heuristic version of this problem should get this right hand column right. Everything else I don't get. At least get the right hand side column right. So it's like saying 3, 4, and 5 still have their numbers written on them, and it matters where they are sitting. Everybody else's numbers have been just whited out. So it doesn't matter whether the other tiles are in random places. As long as you get this part right, then that's the heuristic, that's the abstract problem. Clearly you can understand that the final, if you can get this part right in the optimal way, the number of moves you took to get just this part right in the optimal way is a lower bound than the total number of moves to get everything into the right place. It's a lower bound. Maybe even equal sometimes, in fact, just getting 3, 4, 5 in the right place gets everything else magically in the other places too. But it can never be higher than getting the full problem. You see what I'm saying? So you can decide on patterns and then say for each node I will get the pattern right. That's why it's called pattern database. So to compute that, if I give you this and say how many nodes, how many moves you need to make to get 3, 4, 5 in the right position, it's not very easy to add up some numbers and get it. You actually have to do search. It's a cheaper search, but you have to do the search. So pattern database heuristics essentially compute all for each possible. So again, for the initial state too, you really care about where 3, 4, 5 are and how to get them into the right position. Everybody else is white. That means their numbers don't exist. Okay, they are just basically faceless obstacles. Okay, if you solve that problem, you can basically solve for every configuration of 3, 4, 5 in arbitrary places, and they getting to that place. You can compute the optimal path, put it in a huge big database. You will call this pattern database. When you have to compute the H value of a node, instead of just adding up number of misplaced tiles or adding up the Manhattan distance, go to your pattern database and find the number. And that's still going to be lower bound. And in fact, pattern database heuristics are the only ways you can solve problems like 36 fuzzy. Because the exponent becomes, the cost of the search becomes so high that misplaced tile heuristics and the Manhattan distance heuristics that you are so proud of won't work at all there. And pattern database heuristics came in 90s, even though A-star search was invented in 60s or 70s. That is a community basically having its own biases. Okay, let's stop here.